Good morning, everybody.
Hi, Lydia.
And everybody's wishing you hello, Lydia. Good morning, everybody, and welcome back to Galois Theory. Plan for today, we're going to keep doing a little bit of algebra review, continuing from last time, and then second half of class today, we're going to jump into the new stuff. Start talking about characteristics, because I'm trying to build character for you all in this class. Office hours. Got office hours this afternoon from 1 to 2, and tomorrow from 11 to noon and 1 to 2. Homework 1 has been posted on Canvas. It's due next Thursday because I'm a big softie. Thought about making it due next Tuesday, and then I'm like, some of that is stuff we're not going to get to till Thursday's class, and just make it the week after we don't cover the necessary material. It's 3 questions. I'm going easy on you. I promise I will not always be so easy. But it is up. It is on Canvas. It's an official assignment on Canvas. This is going to distract me very much. And I encourage you all to check that all out, because at the very least you should be able to tackle the first couple problems now. Any questions or comments before we get started for today? In honor of the slippery road conditions out there, what do you call an angle that's been in an accident? Lincoln?
I know this one, except I don't actually remember it, so I guess I don't.
I guess you don't know it then. What do you call an angle that's been in an accident?
Oh,
You call it a.
It's a rectangle.
You call it a rectangle. All right. So with that, let's get cracking. So last time we did a little bit of review on groups, rings, and fields. Looked at a bunch of examples of kind of the standard ones that we were looking at, that we looked at in Math 410, or that I expect you've kind of seen before in Math 410, especially with the groups and rings. The fields, we don't have too much yet. We have Z mod PZ, we have the rationals, reals, and complex numbers, and we're going to be building more fields as the semester progresses. And we talked a little bit about properties of fields, like fields are all integral domains, meaning there's no zero divisors. And if you're an integral domain, for instance, then you have to have cancellation, meaning if you have AB is equal to AC and A is non-zero in a field, or any integral domain like the integers, then B has to be C. Cancel terms out, do the old swoosh swoosh on both sides to them. Other thing we said about fields towards the end of class is that they don't have any interesting ideals. Ideals and characteristics. Well, we are getting into the abstract. Ideals being these sort of subrings that have superclosure. And so what I thought we would start by doing today is to talk a little bit more about ideals and what they're used for, specifically with regards to quotient rings. So with that, let's talk about subrings versus ideals. So, subring, it's like a subgroup. It's just a little ring living inside of a big ring under the same operations. Subring S of R is a ring S that is a subset of R under the same operations as R. Meaning when you're looking at a subring, you have to have the same addition, the same multiplication. So that's to exclude things from like Z mod 5Z is a subring of the integers. Well, no. Z mod 5Z is a ring that the integers are a ring. Z mod 5Z sort of lives inside of the integers under our naive definition of Z mod 5Z is just the numbers 0, 1, 2, 3, and 4, but completely different operations. The rings work in very different ways, so it's not a subring still. Versus an ideal, we could say that subring S is an ideal of R if for all elements little s and big S and little r coming from our ring, little rs has to be an element in S, and little less r has to be an element in S. So in other words, it's a subring that absorbs multiplication from the larger ring. So normally for subring, we have to just have that it's closed under multiplication, meaning thing in subring times thing in subring ends up back inside subring. But for an ideal, we need thing in subring times anything in the larger ring has to end up back inside the subring specifically in order to be an ideal. So what would be an example of an ideal in some ring? Elmer?
The whole ring.
The whole ring. What do you know? Any ring is an ideal of itself. If R is a ring, then R is a ring under the same operations as itself. And if you take thing in ring times thing in ring, you get back inside ring. Yeah. R is always a subring of itself. Famous?
The additive identity.
Ah, the trivial subring. Yep. Yep. The zero set, technically this is the set containing zero, but oftentimes that just gets written as zero as a shorthand. Yeah, trivial subring containing only the additive identity and nothing else is going to be an ideal. It's a subring for reasons we've talked about before, and if you take 0 times anything in the larger ring, you're always going to get 0, and that's a property of, that just comes from the distributive property. That's kind of one of the first things, those of you who had me in 410, that's the first thing we proved about rings, is that 0 element in ring times anything else in the ring will always give you 0.
You say under the same operations as R. So I'm just want to clarify to make sure rings are always just addition and multiplication, right? There's no chaotic anything else.
I mean, yes, but your addition and multiplication could be chaotic.
Okay. Yeah.
It doesn't have to be the usual addition and multiplication. So in Z mod NZ, for instance, it's addition mod n and multiplication mod n.
Okay.
Or like you could have addition and multiplication of matrices,
Okay.
where matrix multiplication is a little bit of a complicated beast. So when we say just addition and multiplication, I mean, that's what we always call the two operations, but it doesn't have to be necessarily what you're familiar with. There's also weird rings out there where like the way you add two elements is the way you would normally multiply them, and the way you would multiply them is you take like 1 to the power of the second. And just say, I hesitate to say, in other words, I hesitate to say just addition and multiplication. Because what do those really mean? Those are just words, man. All right, how about some non-trivial examples of ideals in rings? In other words, I need something that's not going to be true for every single ring.
The polynomials with a 0 constant term inside the polynomials.
Ah, polynomials with a constant term of 0 instead of all polynomials. What's your coefficients coming from? Real polynomials, integer polynomials?
It could be. Just go with reals.
I was gonna say you could pick any of them really, but yeah, we could say for instance, oh gosh, ideal generated by X. We'll talk about what that means in a second. Is an ideal in the ring of all real polynomials. What do I mean by the ideal generated by an element? So in this case, ideal generated by X happens to be the same as the set of polynomials with a constant term of 0. But what does it mean in general to have an ideal generated by something in a ring, Parker?
I would say it's equivalent to multiplying every element of the ring by x.
Yeah, so this by definition is just going to be the set of all elements in the form R times X, where R is just coming from whatever your larger ring is. I guess in this case it would be real polynomials. So it's a set of all real polynomials that have from which you can factor out an X. which happens to be the same as polynomials that have a constant term of 0. And the reason we know this subring forms an ideal, other than the fact that the ideal generated by an element is always an ideal, is if you take something that has, if you take polynomial that's a multiple of x times any polynomial, you're always going to get something that has a multiple of x coming from the first term that you can factor out. So in other words, thing in ideal times thing in larger ring is always still going to be inside the ideal. That makes sense? Yeah, Eleanor?
What about one generated by x and x squared?
Ooh, ideal generated by x and x squared.
I don't remember if that's an ideal.
That is an ideal, in fact. It happens to be the same as this one.
Oh, right. What about 2 and x?
2 and x.
Yeah.
Ooh, that's interesting. That one is actually also the same as this one.
2 and x?
Because we're in the reals.
Yes, we're in the reals, and 2.
It has to be a main
Right.
integer polynomial.
Actually, no, that gives us. Actually, no, it's not the same as that. It's the
It
same
just
as
gives you
that.
the whole thing, yeah.
Yeah, it actually gives the whole thing. Sorry, not the ideal generated by x. If we were working over the integer polynomials, though,
Right.
then we could say, for instance,
Yeah.
Uh,
I mean,
yeah, that was a
I
big.
can tell where you were going with
I was gonna say I knew what she was going for, but yeah. So this would be, for instance, the set of all elements of the form 2 times some r plus x times some s, where r and s could be any integer polynomials that we want. Actually, it's the other way around.
It's just backwards.
I don't know what. I'm sorry, Eleanor's throwing me.
What?
Yeah. And then, yeah, what else does it do? Yeah. This contains, for instance, all polynomials with an even constant term, whereas this only contains polynomials with a constant term of 0. And this is just all integer polynomials, including ones with both even and odd constant terms.
Didn't we call 2x maximal, like in a maximal ideal?
Oh, we did.
Yeah.
Imagine that. What did that mean?
It means that, there's a very specific definition, but it's if you have any subring of a ring, and that subring that you pick is bigger than any other subring that you choose, then that is a maximal ideal, I think. Or no, there's
It's-
another one.
I think it's sort of like what you
It's
said.
sort of like, yeah, I know it's not exactly.
Basically, what it means to say this thing is maximal is to say there's no ideals in this ring that are bigger than it, that include it, except for the entire ring. The only ideal that's bigger is the whole ring. And we'll do a review of like maximal and yes, also prime ideals later on, so you don't have to write that one down right now. We'll come back to that.
So we're saying that like x generates the ideal here. So in theory, if we go back to our definition of the ideal, shouldn't it be that like x and then like multiply by 3x would have to be back in the ideal?
Yep.
So, like how, like,
X-
from my understanding, 3x squared is not back in the ideal.
Is 3x squared not a multiple of x?
But isn't the generation is addition, not multiplication? So it'd be like x,
Ah.
2x, 3x, and then you
It-
multiply those two together.
So like this notation, it does when you're talking about the cyclic group generated by x. And so this comes down to notation being annoying because the same notation is used to mean multiple things. So in group theory, when we have something like this, we just mean A star itself over and over, as well as A inverse, etc., etc. I'm not going to write all that out. But when we talk about rings and use this triangle bracket notation, we mean ideal generated by an element, not group generated, which means something different. In this case, when we talk about ideal generated by an element, we just mean all the multiples of that element within the ring. And you kind of have to know, the Dr. Ursel, how do I know which one it means? You kind of have to know based on the context. Are we talking about Are we talking about the ideal generated by an element, or are we talking about the cyclic group generated by an element? Because that's different depending on whether we're doing group theory or ring theory at the time. Yeah, if we're talking about group generated, then we would just get all integer multiples of x here, which would not be the same as all polynomial multiples of x. But in this case, 3x squared is a multiple of x because it's just x times 3x. Yeah, good question. All right, let me ask you all this. What would be an example of a subring that does not form an ideal?
The rationals inside the reals.
The rationals inside of the reals. Let's see, the rationals certainly form a subring of the reals. They're both rings under the standard addition and multiplication. Let's see, if we take an arbitrary rational times an arbitrary real number, do we necessarily get something rational?
No.
Give me a counterexample.
I don't know, pi times 3/4 is,
That would certainly do it. Pi is real, 3/4 is rational, but the product is 3/4 pi, which is not rational. So we could say this is not an ideal, as for instance, 3/4, 3/4 is in Q, and pi is an element of the reals, but 3/4 times pi is not an element of the rationals. If Q was an ideal of R, then any element in Q times any element in R would have to land you back inside of Q. Since that doesn't happen, we get a subring that doesn't form an ideal. Any other examples? Elmer?
The reals in the complex.
Reals in the complex numbers. Yeah. 2 is in the reals, I is in the complex numbers, 2 times I is not in the reals. And before someone says the integers inside of the rationals, yes, that too. Or the integers inside of the reals, or the integers inside of the complex numbers, or the rational numbers inside of the complex numbers. I think I've eliminated all of those.
Would differentiable functions inside of continuous functions?
Differentiable functions inside of continuous functions. That's a spicy one.
I don't think it's an ideal.
So in other words,
Sure.
you're saying C0R in C1R, continuous functions over the reals inside of differentiable functions. Or
Okay,
the other way
differentiable.
around. Dang it. Okay, look, I'm a little rusty too. Differentiable functions inside of continuous functions. This is certainly a subring of that. Every differentiable function has to be continuous because Calc 1 says so. But anybody think of an example of a differentiable function and a continuous function where the product of the two is continuous but not differentiable? Isaac?
absolute value and the identity function.
That's a pretty simple example, but one I think that works. Yeah, we could say that the identity function is certainly differentiable everywhere on R.
What's the notation for that? Continuous everywhere, but differentiable nowhere. Do that instead.
Want me to pull the Weierstrass function out? I am not pulling that out for this example. Because actually proving that the product of, well,
And the
With the
identity
identity
function.
function.
okay, well, yeah, sure. If you do it with the identity function, sure. But like if you do that times any extremely simple function, and proving that's still, proving that's not differentiable is hard. Yeah, let's go with the identity function. That is a differentiable function everywhere over the rails. Isabel, what's the derivative of the function that's always 1 everywhere?
0.
It's 0 everywhere. And we could take absolute value function, that's certainly continuous over all of R. But you take the product of the two, which will just give us absolute value function back. That is not an element of the differentiable functions over R. Why? Because it is pointy at 0, and sharp and pointy things are bad. I know. You could poke your eye out on that function. Yeah, I did watch that. Yeah, we did watch that at over Christmas break.
What?
Christmas Story. Yeah, that's a little bit more of a spicier example of something that does form a subring, but does not quite give us an ideal. C1R is closed under multiplication itself by the product rule, meaning differentiable thing times differentiable thing is always going to be differentiable, but differentiable thing times continuous thing is not necessarily going to be differentiable. Bit, but not boot. Anybody else have any other examples they want to throw out? Parker?
Would the special linear and the general linear work?
No.
Oh, no.
It's because neither of those are rings.
Oh, yeah, that's true.
Because neither of them are closed under addition.
One that would not be an ideal would be polynomials with degree less than 3 inside of all the polynomials. Or did we already say that?
We did not. So you're saying polynomials degree less than or equal to 3 and polynomials? Let's see.
The first one's not right.
Oh, it's not a ring.
That is not a ring, is it? Closed under addition, but not multiplication.
Rings you can only be greater than
What did I have written down in my notes?
Oh, what about?
Oh hey, we got the ones that I wrote down. I literally had Z inside of Q and C0R and this inside of that.
I swear I didn't. Me.
So she says. So she says. That's my tongue twister.
Even integers inside of Q?
Even integers inside of Q. Sure. Pick any subring, any non-trivial subring of Z inside of Q. Yeah. All right, I'm not going to write that one down. But that gives us some things to go on.
What about QX and RX?
Ooh. And this one?
Yeah.
That's certainly a subring. If you have a rational polynomial and you multiply it by an arbitrary real polynomial, do you necessarily get back a rational polynomial?
No, that's the same reason the Q is not.
Yeah. In fact, literally the same, well, replace this with these with the appropriate polynomial rings, and literally the same example will work to show here's a rational polynomial times a real polynomial whose product is not a rational polynomial. Yeah, so in fact, for very similar reasons to why, before it's getting messy, to why Q is a subring but not an ideal inside of R, polynomial ring over Q is a subring but not an ideal inside of real polynomials. All right, good one. Yes, Eleanor?
What about QI and ZI?
I don't know so.
Gaussian integers inside of the rational complex numbers? Yes, that would work. All right, new topic. Why do we care about ideals specifically? Well, there's several reasons, but that's kind of the main reason why we would care about ideals. Andrew?
They let us do ring quotients.
Yeah, they let us do quotient rings. If y'all remember, for those of you who had me in 410, I promise I won't be saying that all semester long for those who didn't. Those of you who had me in 410, you might remember I made the analogy at some point that normal subgroups are to subgroups like what ideals are to subrings, and that they're a special type of sub-object that is the type of sub-object that we can do quotients with. We can quotient out by an ideal and get something that is still necessarily going to be a ring. So let's take a look at that, because we are going to be dealing quite a bit with quotient rings in this class. So I think it's worth doing a little bit of review. So the elements of the quotient rings are going to be cosets, which you may recall are the same things that we called them in, are the same as they were in group theory. But a coset of subring S of R is a set of the form little r bar, which is the set consisting of some little r plus everything inside of S, which written out using set builder notation is just the set of all elements of the form little r, where little r is fixed, plus any little s, where little s is allowed to be anything in the ideal. And then we had this sort of definition / theorem, which told us if we take the set of all cosets of a particular ideal inside of a ring, that as long as the subring we're looking at is an ideal, then the cosets are actually going to form a ring themselves under wacko coset addition multiplication. I have this listed as a theorem inside of the packet. We're not going to prove this theorem because I kind of assume you've already seen the proof of this in 410 or at least the normal subgroup version, those of you who had me. But basically, this is kind of a part theorem, part definition at the same time, which says that if S is an ideal, the set of cosets which we denote by R mod S, and it's the set of all cosets of the form little r plus big S. Little r can be anything in your ring, is a ring called the quotient ring. Where you can add two cosets, take a little r plus big S, add it to a little t plus big S. You can add two cosets by just taking a coset form by adding the corresponding little r and little t together. And you can do the same with multiplication. Oftentimes, if we use this sort of bar notation, we can rewrite this a little more simply as r bar plus t bar equals r plus t big bar, where the bar just means the coset formed from that element, added to all elements in S, and r bar times t bar is RT big bar. RT bar, Dr. Baltzapf. So, let's look at a couple examples because these are a bit messy. One of the trickier things I think you see in Math 410. We can start out simple. Let's do our ring as the integers, and S is going to be 3z. I was expecting someone, by the way, to say nz inside of z as an ideal, but nobody did. Eleanor, get your name. So, how many distinct cosets is S going to have inside of the integers? In other words, how many integers can we pick that will generate unique cosets for 3Z. Parker?
3,
Give me 3 of them.
0, 1, 2, I think.
Those will do it.
I wanted to say 0, 1, and 5.
We could have picked.
I was afraid he was going to do that. I'm glad he didn't.
I'm a reasonable person. Okay.
Yeah, we could do
It's
0 bar.
not unreasonable.
Yeah, we could do 0 bar, which just consists of you take every element inside of S and you add 0 to it. That's just S. That'll give you 0, plus or minus 3, plus or minus 6, etc., etc. We could take 1 bar, which is literally take everything in S and you add 1 to it. So that'll give you 1 plus or minus 3, 1 plus or minus 6, etc., etc. So 1, 4, 7, 10, 13, dot, dot, dot. Also -2, -5, -8, dot, dot, dot. In other words, integers that are 1 greater than some multiple of 3. And finally, you have 5 bar. Except I'm going to write 2 bar because I like making it easy. If you want to make it harder on yourself, go for it. And it's just take everything in 3Z and you add 2 to it. So 2 plus or minus 3, 2 plus or minus 6, etc., etc. And the cool thing about cosets is they partition the overall ring, meaning every element in the integers is going to appear in exactly one of these cosets. Because every integer is either a multiple of 3, 1 greater than a multiple of 3, or 2 greater than a multiple of 3. No matter what integer you think of, it has to be one of those categories and it can't be more than one without breaking modular arithmetic somehow. So these are kind of the elements of our quotient rings. I often kind of denote these as 0 bar, 1 bar, and 2 bar as just a shorthand notation. But it's important to remember that when you have an element and put a little bar above it, you're forming a coset, which in this case is an infinite set of elements that just happen to be equivalent to 0 mod 3. These are all the integers that are congruent to 1 mod 3. Integers that are congruent to 2 mod 3.
So are all these isomorphic to each other?
Isomorphic as what?
Like, isn't it just like equivalent basically, right? Where they have the same like roles. Like each 0 is isomorphic to like in that.
Usually when you're talking about isomorphic, you're talking about like rings that are isomorphic or groups that are isomorphic. And it's important to keep in mind, this one is a ring, these two are not. This is not a ring because it has no additive identity, it's not closed under addition.
So it's not even a group.
It's not even a group. So typically we can't say these are isomorphic to anything because you don't talk about cosets being isomorphic. You could talk about groups or rings or fields being isomorphic, but not cosets. You can say they all have the same size.
Okay.
They have the same cardinality, which I think is probably the closest you can get to saying they're isomorphic is they have the same size, but you can't really form like a homomorphism, for instance, from that one into that one. What's a homomorphism? We'll talk about that in a second. So, let's do a quick, just because we can. Let's do a couple Cayley tables here, where we do some addition in this group, and we do some multiplication in here.
We did this yesterday, or
Yesterday.
Thursday, whatever day the last class was.
Yeah.
Yeah. And then you were like, let me fill out half of it for you.
Oh yeah, I did.
Yeah.
I was about to do the same thing.
Yes.
But yeah, so basically it comes down to the same thing. Like, hey, if you wanted to take 2 bar times 1 bar, you're basically pick any element in here, multiply it by any element in here, you're going to get something that's in one of these cosets. That'll be in this one, because 2 times 1 is 2, for instance. So 2 bar times 1 bar will just be 2 bar, using that definition down there. And et cetera, et cetera.
Now you're just filling out all of it for us.
Well, apparently we already did this, so I'm not gonna waste more class time filling it out. Here, fill out the addition one yourself.
Use your multiple powers to write on the board.
Oh, that doesn't.
Etc.
Yeah, that gives us, that's how you kind of form quotient rings, is you're forming a ring structure out of these cosets, where you're not just adding individual elements together, you're technically taking entire sets of elements from your ring, and you're adding and multiplying them together by just picking representatives from each one and adding or multiplying the representatives. If you don't have an ideal, if you have a subring that's not an ideal, then these turn out to not be well-defined operations. You can have things like A1 bar equals A2 bar, and B1 bar equals B2 bar, but A1 times B1 bar turns out to not be equal to A2 times B2 bar. It gets weird when you try doing this with something that's not an ideal. So don't, and your life will be a lot happier. Or do, and get involved in some really complex, non-commutative ring theory.
Where do the eyes come in?
When do the what?
The eyes come in.
Oh, they're always there watching you. Mine are, if nothing else. Let's do another example. Let's go back to the good old ideal generated by x inside the ring of integer polynomials. Oh boy. I'm skipping one, yes, if you're following along in the packet, deal with it. So in this case, we're going to take our larger ring is the ring of all integer polynomials, and the ideal that we're going to be quotienting out by is going to be the ideal generated by x. In other words, polynomials with a constant term of 0. We know this is an ideal in here, so we can do some quotienting. So what would addition and multiplication even look like here? Well, we could take, for instance, I don't know. Jackson, what's your favorite integer polynomial?
Or about just the easy one, so x.
X? Give me something with a little more pizzazz to it.
Alright,
At least 2 terms for me.
x squared plus x.
X squared plus x. I'm going to put in a plus 1. I'd rather have a non-constant one. Seamus, give me another one. Make it a non-constant polynomial, but give it a non-zero constant term.
Non-zero constant term, alright. How about 2x squared plus 3x minus 5.
All right. What would happen if we tried to multiply these two cosets together? Well, we'd have to multiply together x squared plus x plus 1 times 2x squared plus 3x minus 5. Oh boy, time to multiply a couple of trinomials together.
Can't we just look at the constant terms?
Oh. What does that equal to?
1
That's equal to 1 bar. What's that equal to?
minus 5 bar. Yeah.
And what do we get if we multiply 1 bar and negative 5 bar together?
Oh my gosh, it's negative 5 bar.
Which means that the answer is 2x squared plus 3x minus 5.
Oh hey, how'd that happen?
Seamus polynomial.
It's almost as though
Is the shape
J-
polynomial?
even after Jackson gave me the 0 element in this quotient ring, I decided to pizzazz it up a little bit and happened to just make it into the multiplicative identity instead of the additive identity. If I didn't, you would have just gotten 0 bar, no matter what Seamus's polynomial was. And so it happens, you can actually do these sort of computations a lot easier inside of this room.
Jackson had a winning polynomial, but you took it from him.
I what?
Jackson had a winning polynomial, but you took it from him.
I took it from him. Apologies, Jackson.
We'll do it next time.
I mean, he just wanted to have X bar. I mean, I wasn't gonna let it get away with that because I wanted something you couldn't just easily multiply in your head. That's the whole point of this. Keep in mind, this is a set of all elements of the form x squared plus x plus 1 plus s, meaning everything in this coset consists of some non-constant polynomial plus x squared plus x plus 1. This is a set of all x squared plus x plus 1 plus g of x, satisfying g of x, or g of 0 happens to be 0. Which in turn happens to just be the set of all elements of the form 1 plus h of x, where h of 0 is 0. Why is that? No, it's just because we can take the x squared and the x and we can kind of fold those into the g of x, because they happen to also be terms that if you plugged in 0 for x, you'd get 0 as your output. Andrew?
No, sorry.
Oh, that looked like it. I've been deceived. So, turns out, if you look at this quotient ring, R mod S here, or in other words, integer polynomials modded out by ideal generated by x, turns out any coset can just be reduced to a constant term. And so multiplying cosets in this quotient ring behaves an awful lot like just multiplying two integers together. Addition is pretty similar. You just reduce it out to the constant term bar and add the integers. So it's almost as if this ring behaves an awful lot like the integers, huh?
Maybe we should make a homomorphism or an isomorphism between this ring and the integers.
We did that in 410, didn't we?
Yeah.
Oh, hey!
There's probably.
I assume we, yeah, we did. I stopped thinking.
I don't remember if it was a homework or in class.
Pretty sure we did that in class. Let's do it again though, just to remind everybody. Turns out these are isomorphic. What does that mean? Intuitively, it means that mathematically they behave the same way. Any interesting property that one ring has, the other is going to have as well. Like they have the same cardinality, the same elements, number of elements of every order, etc., etc. Multiplication, addition work the same way. Practically, or more concretely, what does it mean to say two rings are isomorphic to each other?
You can make an isomorphism from one ring to another ring.
Yeah, we can form an isomorphism, a function that is a homomorphism, meaning phi of A plus phi of B equals phi of A plus B, and phi of A times phi of B equals phi of A times B. And it's one-to-one, meaning no two inputs map to the same output. And it's onto, meaning every element in your codomain gets mapped to by something from the original domain. Oh gosh, that looks awfully tedious to do with a quotient ring like this. Is there any easier way to show we have an isomorphism here, rather than finding one directly?
Maybe what if we find a homomorphism between Z and the polynomials, integer polynomials?
Just a homomorphism from one? Okay, the trivial one. I found one.
Whose kernel is X?
Oh, whose kernel is the ideal generated by X? I assume you wanted to go the other way around it, but okay. And what else does that thing have?
Well, the image has to be the integers, doesn't it?
And that's onto, so the image is all integers. Huh. What theorem are we going to be using here to arrive at such a result?
We will be fit.
The first isomorphism theorem, or fit, yes. And anytime you want to prove quotient thing is isomorphic to some other thing, you're probably looking to use the first isomorphism theorem. And that's going to be an important one for us this semester, so I thought we'd work through an example together for old time's sake.
Aww. We both did the same.
Oh, that's so sweet, I Dr. Goisto. So, here's the first isomorphism
So
theorem,
sentimental.
which I made an argument in 410 for this being the most important theorem of the semester. It's not going to be the most important theorem of this semester, I'm sorry to say. That would be the fundamental theorem of Galois theory,
Oh, that's an absence.
which is probably we're not getting to until like April. But
That's kind of sad.
we could what?
Do it on my birthday.
When's your birthday?
I don't know if it's on a Tuesday or Thursday, so that's
All right, I have to look. What's your birthday?
April 13th.
You're kidding, that's 2 days before mine.
Oh my
That's not
god.
Oh,
Oh, I hope it's a Tuesday, so both of yours.
No!
It's a
That
Saturday.
means I'm on a 1 day.
Oh, well then, doesn't work.
Uh,
Sorry.
It could
We
be
are
way
not
worse
celebrating.
though, because I mean, you've already taken a bunch of algebra before you ever hear the fundamental theorem of algebra.
I mean, I don't know. All right, so we're gonna let phi from R to R prime be a ring homomorphism.
No, because this was, focus, yeah.
Then R mod the kernel phi is gonna be isomorphic to the image of phi as rings. What's that be?
Sorry.
You should be.
I was trying to figure out, I missed the April 14th and February 14th. Because I knew February 14th was a Wednesday.
Oh.
In my head, I was like, oh, it's
Okay,
April.
so then
And then that
add,
would make April 13th.
let's see, this
Tuesday.
is a leap year. This is a leap year, isn't it?
Yes, it is.
Oh,
Okay, so then 29 is 1 mod 1 mod 7, so add 1 day to that, and then March is 3 mod 7. 31 is 3 mod 7, so add 4 days past whatever February 14th is, that should give you April 14th. Boom, the power of modular arithmetic. But anyways, let's get back to this. So, first isomorphism theorem was this swanky theorem that told us if you have a homomorphism from one ring to another ring, or if you replace rings with groups here, this also works for groups, then R mod the kernel of a homomorphism is always going to be isomorphic to the image of the homomorphism. So, time out. What does all this stuff mean? So first of all, let's start with ring homomorphism. What does it mean for a function to be a homomorphism of rings?
There's a function that's one-to-one in operation preserving between them.
It doesn't have to be one-to-one. One-to-one is a separate thing. But operation preserving, I like that. What do you mean by operation preserving?
You can either compose two elements and then map them to the function, and you'll get like the equivalent thing, or you can map them and then combine them on the other end.
You can. If you add and then plug into phi, you get the same thing as if you plug both of them into phi first and then add them in the second ring, and ditto with multiplication. In other words, we need that phi of a plus b is always equal to phi of a plus phi of b. If you add a and b in the first ring and then map to the second ring, you get the same thing as if you plug in if you map a and b into the second ring and then add them using whatever your operation is in ring 2, or R prime here. And ditto with multiplication. We want phi of AB to be equal to phi of A times phi of B. So, yeah. Short, in other words, it's an operation preserving map, one that respects the addition and multiplication structures of the two rings. And that if you add or multiply, then plug in to the function, you get the same thing as if you did it in the opposite order. Okay, what's the kernel of phi? Parker?
It's all that stuff that maps to 0 when you plug it in.
Yeah, it's going to be the set of all elements A in your first ring, such that phi of A is equal to the 0 element. Technically, this is the 0 element of the second ring, R prime.
It's not an isomorphism if there's more elements in
Well, it can be. Oh, okay, I see. Never mind, I misinterpreted what you said. I thought you said like the number of elements in the kernel there. It's like, no, there has to be one element in the kernel.
No.
And it is the 0 element, that's what you meant. How about image?
That's all elements in R prime can be written as phi of some R in the first R.
It's a set of all elements R prime that are equal to phi of some element coming from the first ring. In other words, it's the range of the function. It's all the things in your codomain that actually get mapped to by something. It's a set of all R prime that are equal to phi of R for some R coming from the original ring. And finally, what does that mean? Lakin.
Is isomorphic to.
Cool. How do you show two things are? What does it mean for two things to be well, I've kind of already answered that. All right, fine. Yeah. So is isomorphic to means that it's a homomorphism. You can find a 1-to-1 onto homomorphism from one to the other, which is a structure preserving map that happens to also be onto and 1-to-1, meaning it kind of everything in the first set gets mapped to a unique element in the second set, and everything in the second set gets mapped to by something. So let's use fit here. Prove this. So we want to show that integer polynomials mod ideal generated by x gives us a quotient ring that's isomorphic to the integers. Two ways to do this. One, we can directly find an isomorphism between the two sets, which is a pain to do because you have to show it's well defined in addition to being a 1-to-1 onto homomorphism. So actually directly finding a function from this thing to this thing that's an isomorphism is hard. So we're going to use fit instead. And just say, we're going to find some ring homomorphism from this ring, this here being the R, and this being the R prime, for which this we want to be the kernel of phi, and we want R prime here to also be equal to the whole image of phi. And if we can do that, then fit would come into play and say as long as our map phi is a ring homomorphism, fit will tell us the quotient ring is isomorphic to the integers. So how do we do that? So what would be a function phi going from integer polynomials to the integers that's homomorphism? Oh, you can clap. You can clap with us. Okay, what was I saying? How can we find a homomorphism from integer polynomials to integers whose kernel, in other words, the set of things that get mapped to 0, is the ideal generated by x, and whose image is all integers? Oh, Emily Rose?
Map to the value of the constant term.
Yeah. We could say phi of x. P of x just maps to P of 0. I think that'll get the job done. So, Eleanor, we have to prove several things about this function in order to be able to use fit here. What do you want to prove first?
Kernel is the
Ideal generated by x?
Yeah.
Okay. So let's look at the kernel. So the kernel of phi by definition, is the set of all p of x that satisfy phi of p of x is the 0 element in the integers, just literally just the integer 0. If phi of p of x is p of 0, by definition, this will be the set of all polynomials, integer polynomials, where p of 0 is equal to 0. And Isaac, what do we know about the integer polynomials where p of 0 equals 0?
They all have a constant term of 0.
They all have a constant term of 0. So what do they all have as a factor? What can you? They're all multiples of x. And in fact, that just gives us the ideal generated by x. Okay, neato burrito. That's one thing down. What else do we need to show about this function phi? We've shown one of the things, that the kernel is the ideal generated by x. But there's a couple other things we need to show. Get other students involved too. Matthew?
And who?
Can we just show the image too?
We want to show the image of phi is what?
All the other integers.
Yeah, we need to show that the image is made up of all integers. In other words, we need to show that phi is onto. So if we do that, we'll get the image of phi. Or let's not do it that way. Let's just prove it's onto, because that's the same. That means the same thing. So given any integer n in the integers, can we find some polynomial that'll map to it? Isabel?
Sorry.
Sure. If I were to give you some arbitrary integer n, what would be a polynomial that would map to that n?
1 or x.
Well, x would map to 0, because if you plugged in 0 for x, you'd get 0. Let me ask you this. If p of x is getting mapped to its constant term, what would be a polynomial that is a constant term of 3?
3. Sorry, I'm confused.
Well, 3x has a constant term of 0, right? Because you can write it as 3x plus 0. I think x plus 3 would be would have a constant term of 3, because the term by itself with no x's in it is a 3, right? What would be a polynomial, Isabel, that has a constant term of 7?
X plus 7.
How about a constant term of 5 billion?
X plus 5 billion.
How about that as a constant term of n?
X plus n.
There we go. Given any element in our codomain, any element in the integers, we can always find some polynomial back here that will map to it. Any n will get mapped to by x plus n. If you wanted to be cheeky, you could say, oh, it gets mapped to by 27x cubed minus 5 billion x squared plus 16x plus n. And that would also have worked. If you really wanted to get cheeky, you could just say, oh, n equals phi of n.
Yeah.
That works too. But I like your answers. Not completely trivial, but it's also not super complicated.
X to the 240th plus n.
Yeah, that's why I didn't ask her.
X to the n plus n.
And it's in the image of. And this tells us that phi is. Alright, there we go. Alright, so we've proven that the kernel of phi is what we want it to be. We've proven that the image of phi is what we want it to be. There's one other thing we have to prove about phi, though, before we can just say, and by fit, we're done. Jonah?
We need proof that the quotient is well defined, so that the kernel's an ideal.
We need to prove the quotient is well defined.
Don't we need to show that the kernel's an ideal? Or
I mean, I mean, it's ideal generated by x, that's an ideal. What do we need to show about phi specifically? The function.
That is 1 to 1.
It's very much not 1-to-1, so I hope we don't need to prove that.
Just kidding.
Int. X squared,
Oh,
phi of x
yeah.
squared equals, phi of x equals 0, so they boom,
Yeah.
not 1-to-1.
Just
So not 1-to-1, and we're not directly constructing the isomorphism, we're just using fit, which requires an onto, but probably not 1-to-1 function.
We need a homomorphism.
And we need to show phi is a homomorphism in order to be able to apply fit, because if phi isn't a homomorphism, none of this applies. So let's do that. Say what?
That was confusing me, because it looked like we already had it up there.
Oh yeah, no, this is just kind of hey, what are the different parts of what the theorem statement means? All right, Isaac, 2 things to do to prove phi is a homomorphism. We have to do that it's a homomorphism with respect to addition and multiplication. Which one do you want to start with?
Addition.
And they're both basically the same. Yeah. Okay.
Both at the same time.
Yeah.
That would
P
be
of
more-
x.
That's more fun.
No. Q of x is equal to, well, what's the constant term of p of x plus q of x?
Q0 plus Q0.
P of 0 plus q of 0 equals phi of p of x plus phi of q of x. Oh.
whoa.
That's kind of
Okay, it's not that exciting.
That's a bit bonanza.
Alright, let's do product. If we were to multiply p of x and q of x together, we're going to get a mess. If p of x and q of x are not monomials, single term. But what's the constant term of p of x times q of x going to be, Andrew?
P of 0 times Q of 0.
Yeah. If you're multiplying 2 polynomials, the constant term of that product is just going to be the product of the constant terms from the original polynomials. Everything else is going to have at least one factor of x in it. So we'll get p of 0 times q of 0, which is a phi of p of x times phi of q.
Oh my god.
Phi is a ring homomorphism.
Whoa. That's a little wacky.
Why are you never? I'm sorry, Parker. Are you having problems from sitting so close to the front of the room?
No, I can see you just fine.
All right,
I can move.
guys. Let's write this in this tiny corner up here.
Wait a minute. Wait, let's write it right there.
Okay, so we've proven phi is a ring homomorphism. We've proven it's onto, so the image is all of z. And we've proven that the kernel is the ideal generated by x. Is there anything else we need to prove? Why no, Jonah, there's not anything else we need to prove here. We can just use fit at this point and say, by fit, this mod, the kernel of phi, has to be isomorphic to the image of phi, which is the same as saying we know that the kernel is the ideal generated by x, and we know that the image, from the fact that phi is onto, consists of all integers. And that gives us the isomorphism we want. Neato Dorito. Any questions or comments related to that? Yes, Lincoln?
So, sorry, what are actually the conditions where you have to prove the well-definedness of,
That would be if we were trying to directly define a map from the quotient ring to the integers. Like if we were trying to come up with like
okay.
psi from that actually takes in cosets as inputs and spits out integers, then you would need to check well-definedness. Anytime that your domain consists of cosets, well-definedness is something you need to do. Which we had to do that as part of our original proof of the first isomorphism theorem, to show the first isomorphism theorem works. But if you're using fit and not trying to prove fit, typically you pick your ring R to be something that's not itself a quotient ring. It's usually just whatever that is. And as long as your domain is not made up of cosets, then you don't need to worry about checking well-definedness. And the well-definedness comes from, if I pick two different representatives from the same coset, do they necessarily, to represent the coset, doesn't necessarily map to the same output, is where that occurs.
Can you have a quotient ring of a quotient ring?
Sure. That's the third isomorphism theorem.
Oh, what's the second one?
I always forget the second one because it's not very important. You know the third one, really? Or the fourth one's actually a little more interesting.
What? How many are there?
Four that I know of. I'm sure people have come up with more and labeled them, oh, I have the fifth isomorphism theorem. But there's like four standard ones. The third one is basically like if H is a normal subgroup of K, I'll give you the group version, is a normal subgroup of G, then G mod K mod K mod H is isomorphic to G mod H. And
We did that, didn't we?
Oh, we did do that.
We did that.
Yeah,
I think we talked about it, I don't know if we
We talked
proved it.
about it.
I think
yeah.
it was on.
We did it on homework.
Yeah.
Oh yeah, it was on the homework.
Yeah.
But it's
You
basically,
just didn't tell us it
That
was
was
the
so
third.
easy though.
which is basically,
Did we actually do that, or was it just about?
Yeah, we did that.
That makes up with ECAC.
no, it's this. It's G mod H mod K mod H is isomorphic to G mod K.
I think that's still what we did on that one.
Yes.
Yeah, it is.
Okay, yeah, it basically is the one that says, hey, if you take G over H and you multiply by H over K, hey, look, you get G over K.
Cancellation rules.
It's sort of cancellation, but actually applying to cosets in this much larger sense. The second isomorphism theorem is just a specific subcase of the first one that applies, I think, when you're doing like intersections of subgroups and subrings and such. I forget what exactly it says offhand. The fourth one is the lattice isomorphism theorem, it has a second name, and that one is a fun one we might be talking about later on, so I'm not going to say too much.
It's crunchy. Lattice isomorphism.
Crunchy.
Does there always exist an isomorphism or a homomorphism for if there is like a ring with an ideal where the ideal is always the kernel of that new
Yes, actually, that's kind of a cool result about ideals is that like a subring is equal to here, make some room for myself. If H is a subring of let's say S is a subring of R, we have a theorem that says S is an ideal of R, shorthand for ideal, if and only if S is equal to the kernel of some homomorphism phi from R to some other ring. Because in other words, the kernel of a ring homomorphism is always an ideal, and if you have an ideal, then it's always going to be equal to the kernel of some ring homomorphism from your larger ring to some other ring. You can also replace the word ideal with normal subgroup and say the same thing about normal subgroups in group theory. That a subgroup of a group is normal if and only if it's equal to the kernel of some group homomorphism.
That's crunchy.
It is crunchy. Those of you who had me, I think we proved the group version, but not the ring version.
Yeah.
But it's a very similar sort of idea.
Is R prime unique?
Not necessarily. When we say for some ring homomorphism R to some other ring, that homomorphism and that R prime need not be unique.
Okay.
I don't even think it's unique up to isomorphism necessarily.
Because you can have more than one ideal, I suppose.
Well, I mean,
More than one.
yeah, I
Yeah,
guess
you can-
I mean that's isomorphic.
I don't think it has. I don't. Actually, is that a universe?
Probably state the first isomorphic.
I
simply.
don't actually know that.
Does each ideal have its own like mapping and its own associated kernel?
Yeah.
Oh wow.
look back at your 410 notes, see how we constructed that. I don't know the answer to your question, I'll have to think about that. Andrew, you think it does have to be unique?
I mean, that's my gut, that
Well, cause.
Well, 'cause if there's multiple
I feel like if you
ideas.
just.
No, because you can always embed this into something else, into some bigger ring.
Well, and function-
Yeah, so it does, yeah, and if it's
Yeah.
a strictly bigger ring, so no, it doesn't have to be unique.
That's fair, yeah.
But like, does it have to be unique up to isomorphism into some embedding into some larger ring?
Well, then
They're minimum.
then you're pretty close, cause then you've got the image part of that.
Right.
And we already stated the kernel part, so then
Right.
then you would be saying the same thing as the first isomorphism.
Yeah, okay. I think so, you're right.
So,
By the way,
Yeah.
second, third, and fourth isomorphism theorems, before I forget, you prove them all of them using the first isomorphism theorem. They're really all special subcases of the first isomorphism theorem in special circumstances.
It's the isomorphism theorem and three nice corollaries.
Pretty much, actually. I don't know. I like that one just because the whole invert and multiply by fractions is kind of fun. Mod H mod K mod H plus mod D mod K. And that is primarily when you see quotients of quotient things showing up. True for both groups and rings, by the way. Replace normal subgroups with ideals as needed. Yeah, that's sort of it for the introduction to this course. Any obviously that's not everything we did, and like you probably have seen in abstract algebra. There's a lot more with regards to things like specific groups and specific rings that we did. Like we did talk at all about like permutation groups, or the dihedral group or the symmetric group or whatnot. Which those will come into play later on in the class, and and there's some ring theory ideas like maximal and prime ideals that I don't know if you've all necessarily seen in 410 because it kind of is like a very end of the course sort of thing. But those will come up and we'll do some more review as the semester goes on. But starting in next class, so Thursday's class, I want to get into some new stuff. The example I skipped was what?
kind of crazy.
It's kind of crazy. What was that? Reals mod integer polynomial. Real polynomials mod integer polynomials. Yeah, it's crazy as a quotient ring. Yeah, I was just planning on doing an example of like, hey, here's what happens when we add two cosets together. And hey, this sort of weird bar thing happens where the non-integer, where the bar is reduced to just the non-integer parts. So like pi x cubed plus 2x plus 1 bar is the same as just pi x cubed bar because 2x plus 1 is in the integers.
I'm trying to figure out the
Most
cardinality of
people
it.
here who are interested in math competition